Welcome to another video in a series on the xv6 operating system kernel. In this video, I'll be talking about pipes, and I'll do a code walkthrough of the file pipe.c. Remember that in Unix, a pipe is a little bit like a file. You can write data to it and you can read data from it. However, a file is kept on disk while a pipe is entirely within memory. So here we have a process, let's call it W, writing data to the pipe, and some other process, R, can be reading data from that pipe. The data is kept in some buffer inside the kernel's memory, and that buffer has a limited size. So if process W writes too many bytes, the kernel will need to suspend it until the buffer is no longer full. And likewise, if process R tries to read bytes, but there are no bytes yet sitting in the buffer, then the kernel will need to suspend process R until process W writes some bytes into the pipe. For every open pipe, the kernel will allocate and use exactly one structure of type pipe, which I'm showing here. So this structure has a spin lock, and that spin lock protects all the remaining fields in the structure. It has a buffer, and that buffer is 512 bytes in our case. The actual size is determined by a constant, which is defined to be 512. And it has two indexes, read and write, which tell where in the buffer we are, and a couple of Boolean flags called read open and write open, which I will discuss a bit later. Now, with inodes, the kernel maintains a cache of inodes, some of which are free and unused. And whenever we want to allocate a new inode, we search through that array and find an unused inode, and then we allocate it and use that one. With pipes, things are done a little bit differently. Instead, we don't have a cache or an array of unused pipe structures. And whenever we need a new pipe structure, the kernel will call kalloc and allocate an entire page. And then when it's done with that structure, it will return that page to the free pool. Remember that our pages in xv6 are 4K bytes in length. So the structure itself will occupy just a little bit more than half a K. The remaining almost 3.5K of the page will simply be unused and wasted. For a production operating system, you might want to think about a slightly different organization, particularly if you think that we are going to have a lot of pipes. But for xv6, we're not going to have so many pipes, and this is quite practical. Now, next I want to talk about the code here and show that the code corresponds to this exactly. Here we have the spin lock. Here's the definition for the structure pipe coming from file pipe.c. And we have the spin lock, we have the buffer of size, pipe size, we have the two indexes, and we have the two Boolean flags here. How are these indexes used? Well, the inRead tells where in the buffer the next byte to be fetched for the reader is, and the inWrite index tells where in the buffer we should put the next byte that is written to the pipe. And so here in red, I'm showing that this buffer contains several bytes, and we will add to the buffer at this point, and we will retrieve from the buffer at this point, advancing the pointers. This buffer is a circular buffer, so before we access the buffer, we are going to take the value modulo 512. So we have a wraparound situation. Here's another situation where we have 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes in the buffer, and they wrap around here. You can think of the buffer as an infinite sequence of bytes. So inRead and inWrite can be advanced well beyond 512. In other words, we can write thousands and thousands of bytes into the buffer as long as we keep up with the reading and never have more than 512 bytes in the buffer. So these two situations are equivalent views of the same situation. An empty buffer situation will look like this. whenever the read index catches up to the write index, we have an empty buffer. Okay, the next character or the next byte that we're going to write into the buffer will go into this position, and inRead tells where to read it, and we haven't written that byte yet. When the buffer is full, we have a full 512 bytes in the buffer, so the write pointer will exceed the read index by exactly 512. And we can think of it this way, or we can think of it this way. Now, in the past, I wrote some code like this, and I performed the modulo operator before storing the indexes. So these indexes would only range from 0 to 511. And that's really not a very good way to do things, because it makes the empty situation identical, or appear to be identical, to the full situation. So it would require some other data. When reading the xv6 code, I realized that this is really a much better way of doing things. So we allow inRead and inWrite to exceed 512, perhaps by quite a lot. And we only take the modulo operator before accessing the data in the buffer. And this is a superior way of doing things that I learned by reading the xv6 code. And that points out that you really can learn new tricks by looking at the way someone else does something, that is, by reading other code. Okay, next let's get into talking about how this pipe structure is used. We'll begin by assuming that we've got a process called P. Every process is represented by a proc structure, and this object right here is used to represent process P. A process can have a number of files open at any one time. The user code refers to the individual files using a file descriptor. The file descriptor is a small number, 0, 1, 2, and so on, and it's used as an index into this array by the kernel. So within the proc structure, we've got this O file array, and it contains pointers to file objects. So for every open file, there is a pointer in this array, and it points to this file object. And of course, the user process doesn't get to use pointers in the kernel space. Instead, it passes in a file descriptor. So for example, if it wants to read from file number 2, it passes in a 2, and the kernel will then follow it to this file structure. Here it looks like we've got all the file descriptors in use, but if some of the files are closed and these entries are unused, then there would be a null stored in that particular entry. The file object starts with a type field, and I'm going to be talking about pipes, so the type for this example is pipe. But in most cases, the file structure is going to point to an inode. So in any case, the file structures contain a pointer, and that pointer will point to some object. It could be a pipe, or it could be an inode. Normally, it would be an inode for a regular file or directory. There are also a couple of flags, the readable flag and the writable flag, within the file structure to tell whether the file can be read or written, or perhaps both. In the case of a pipe, we have two file structures. Okay, we have one for the read end and one for the write end. And so the file structure for the read end, well, it would have a type of FD pipe, and the readable flag would be true, but it would not be writable. And for the write end of the file of the pipe, we would have a file structure, again with type FD pipe, and it would be marked writable, but not readable. And so we can have two pointers, or we will have two pointers pointing to the pipe, and two file structures, one for each end of the pipe. Now these file structures contain a reference count too. I didn't show it here, but the file structure can be pointed to by a number of different processes, right? This one particular file could be opened by lots of different processes, and so we have a number of different pointers here, and the reference count keeps track of those. And when it goes to 0, we can reclaim the space used by the file structure and add it back to the free pool. The pipe structures, on the other hand, will have exactly two pointers pointing to them. So in the pipe structure, we have these two fields that I showed earlier, the read open and the write open flag. And so the read open flag will be true if and only if there is a file object pointing to this pipe structure. And likewise, the write open flag will be true if and only if there's a file for the right end pointing to this pipe structure. And when both the read open and the write open are false, we can say there's no pointer pointing to this pipe object, and then it can be returned. In that case, we would go ahead and free the entire page that it sits on by calling the kFree function. Okay, so what I want to do is assume that this process P has called the pipe system call to create the pipe and to allocate two file objects and set up these pointers. So after the pipe system call, this is the situation we have. The system call will find some empty slots in the file descriptor array, and it will use those, and it will return those numbers, in this case 2 and 4, to the user mode process, so it can refer to either the read end or the write end. Now let's assume that this process forks a couple of children. One child will be a reader process, and the other child will be a writer process. So whenever we fork a process, we make a full copy of this array. Okay, so we copy all of the open files. So if a file was open in the parent, it will be open in the child. And so initially, both pointer 2 and pointer 4 here will be set to point to these two file objects. But we're going to assume that the reader process immediately closes the write end. So we decrement the count to this, the reference count for this object, and set this pointer to 0 because that pointer no longer exists. And process P is also going to fork the write process. And again, the entire O file array will be copied and the reference counts increased for all the file objects. And then we're going to assume that process W will immediately close the read end. So we'll end up following this pointer, decrementing the reference count, and then setting that to null. So now we have this situation. By the way, my indexes don't quite line up here, but I think you get the idea. So at this point, we have this situation where process R points to a file object for the read end of the pipe, and process W points to a file object for the write end of the pipe. The parent process still has these pointers, and perhaps it will go ahead and close them or not, but I don't know. But in any case, at this point, process W can send data to process R by issuing a system call, a write system call, on the file for file descriptor 4, while the reader can read data from the pipe by issuing a read system call using file descriptor 2. So here is the pipe allocate function, and what it's going to do is allocate the pipe structure and these two file objects and return pointers to the two file objects that were allocated. So it has to return two pointers, so that's done as follows. The first argument, f0, is a pointer to a pointer, and that's for the read end. And the second argument is another pointer to a pointer for the write end. And you can think of it this way if you're not familiar with this pointer to pointer stuff. F0 points to an area where we will store a pointer to the read end file object, and F1 points to an area where we will store the pointer to the other file object that we allocate. And this function will return 0 if everything's okay, and -1 if there's a problem. So we start by initializing these two variables to 0, okay, so that they don't point to anything. And then we call file alloc to allocate the read end and save that in this variable here. And we call file alloc again and save the pointer to this object in this location here. And if there was a problem with either of these and we get null back, then we're going to go to this bad label down below where we clean up. And the next thing we do is we call kalloc to allocate a page in memory. And if there's a problem with that, again, we get a null back and we go to bad. Now, if we go to bad, let's take a look at the bad label down here. We basically need to clean up. So we check to see whether we've allocated either of these file objects. And if we've allocated the read end, well, we call file close to get rid of it. And if we've allocated the write end, we call file close to get rid of it. We have this code here that checks PI, that's the pointer to the page that we've allocated. But if you look at this code, I don't think you can ever actually call kFree here, because PI is set to 0 here, and if we go to bad here, PI will be 0 and it won't get executed. And likewise, the only way we can take this jump is if kalloc returned null, in which case PI will be 0. So I think this test is actually superfluous and cannot actually be used. But in any case, moving on, the next thing we do is we allocate the pipe structure. So remember that we have a number of fields in the pipe structure that we need to initialize. We need to initialize the spin lock, as well as the 2 indexes into the buffer area, and these 2 flags. And we're doing that right here. Here we are initializing the 2 indexes, here we're initializing the 2 flags, and here we are initializing the lock associated with this pipe. Then we need to initialize the 2 file objects. So for the read end, we set its type to FD pipe, and we make it readable, but not writable, and we set its pointer to point to the pipe object that we just allocated. Then we initialize the write end, so we set the type to FD pipe, and we set it to writable, but not readable, and again, we set its pointer to point to the pipe object. And finally, we return 0 because everything's okay. Here is the pipe read function. In addition to the pipe allocate function, there's also a read, a write, and a close function. So we only have those 4 functions to deal with. The pipe read function is passed a pointer to one of these pipe objects, as well as an address and a byte count. This address is a virtual address, and the byte count tells us how many bytes we want to get out of the pipe at most and place into the user's virtual address space. This function will return the number of bytes that we actually read, and this could be 0 if the pipe has been closed down. And if there's a problem, it might return -1. Okay, since we're going to be accessing the counters, the in-read and the in-write counters, we need to first acquire the spin lock that protects this pipe structure. So we acquire that lock right here. And then in this loop here, we are going to be checking to see whether the pipe is empty, right? We have 2 situations that we need to watch for. One is whether the pipe is empty, and the other is whether the pipe is full. If the pipe is empty, then the reader will have to go to sleep and wait for a writer. And if the pipe is full, then a writer would have to go to sleep and wait for a reader to take some of the bytes out of the pipe. So here we're checking to see whether these 2 things are equal. And if the 2 indexes are the same, we have a situation like this, where we have an empty pipe. So if we still have a writer, okay, then we will go to sleep and wait for that writer to put something in. If we don't have a writer, then we've got a problem. There's no point in going to sleep. If the write open is false, it means there is no file object that is pointing to this pipe, and so no bytes will ever be written, and we will never be awakened from any sleep we would do, so we better not go to sleep. Instead, we'll just return 0 down here. So let's say that the pipe is empty and we do have a writer, then we will go to sleep. Okay, so the sleep needs a channel, and the channel number that we're using, that is the code or identifier that we're using to the sleep function, is the address of the read index. So we're passing it the address of the read field within the pipe structure that is currently empty, and that will be the channel that the writer will wake up on. It will issue a wake-up call using this channel to wake up this process. When we call sleep, we need to be holding a spin lock, and we are holding the spin lock, and that will be momentarily released. But then when we are reawakened, it will be reacquired, and we'll loop back and again check to see whether the pipe is empty. It could be that some other process is another reader and grabbed those bytes, and then the pipe is still empty. So we make these checks again, and assuming that there are bytes in the pipe, then we can proceed down here. Before we go to sleep, we also check to see whether this process has been killed by some other process. So we're grabbing a pointer to our proc structure, and we're checking the killed field here. And if that's been set to true, then we need to, terminate after the system call that's involved with this pipe reading. And so we immediately release the lock and return -1 to indicate that something is wrong. Okay, so assuming that's not the case, we go to sleep, eventually we wake up and we find that either the file is no longer empty or there is no writer anymore, in which case we need to go ahead and return something. So what we're going to do is we're going to loop through each byte. We need to find up to n bytes, and we're going to ultimately return the number of bytes that we have transferred. And we're going to transfer each 1 byte at a time. So we check here to see whether the pipe is empty. We could get to this situation after looping through this a couple of times, in which case we've emptied the pipe, or it could be that on the first iteration we got into here because there's no writer, and so the pipe is empty, and furthermore there's no writer, so in that case we need to return 0 immediately. But normally we would get at least a couple of bytes, so I will not be 0. So if the pipe has something in it, then what we're going to do here is we're going to go to the buffer area in the pipe structure using nread as the index. And remember, it's a circular pipe, and so we need to do mod the pipe size, which happens to be 512. And then we use that as an index to grab a byte of data, advancing the index, and we save the byte in ch. And then we're going to transfer that 1 character to the virtual address space. So that's the copy out function right here. It's passed a pointer to the page table that describes the user's virtual address space, as well as where we want to place that byte. So this is the virtual address, that was our argument here, offset by how many bytes we've read. And we are passing a pointer to the byte that we just retrieved, as well as a byte count of 1. And if that works okay, then we loop back, but otherwise we break out of this loop and we're done. In any case, we have read bytes. Well, maybe we haven't actually retrieved any bytes and incremented the nread. It can't hurt to wake up a process, but in any case, we must be sure to wake up any writers because we have probably removed some bytes from the pipe, and so the pipe is no longer empty. So we use the address of the write index for the writer. So while readers will sleep on the read index and wake up on the write index, writers will sleep on the write index and wake up on the read index. Well, and after waking up all waiting writers, we will release the spin lock and return the number of bytes that we have moved into the user's virtual address space at this line. Okay, next let's move on to the write function. Here is the pipe write function. Like the pipe read function, it's passed a pointer to the pipe structure as well as an address and a byte count. The address is a virtual address in the user's address space, and n is the number of bytes to transfer from that virtual address space to the pipe. It returns the number of bytes that have been moved into the pipe. In the case of pipe read, the number returned may be less than the desired number. The pipe read function will try to read at least one thing, but will return after getting at least 1 byte if there is nothing else waiting in the pipe. On the other hand, pipe write will try to write all n bytes and will normally return n. If there's some sort of an error, it may return -1. And if there's a problem with the page table, it might return a value less than n, but normally it will return all n bytes. So the structure of this function is a loop, and each iteration of the loop will try to move exactly 1 byte, and that happens right here. And we increment I. So I starts out as the count. I is the count of bytes that we have moved, and it will keep being incremented. And ultimately, when we exit this loop, I will be equal to n, and we will return n, the number of bytes moved. It may be that we exit prematurely if there's a problem with the page table, and we return a smaller n, smaller value than n. So let's take a look at this. First of all, we check in the body of the loop to see whether we have any readers. If the read open flag of the pipe structure is false, then there are no readers, so we immediately return -1. Likewise, if we have been killed, then the killed field of this process will have been set, and we need to abort immediately and return -1. But in either case, we release the spin lock first before returning. So assuming everything's good, we next need to check to see whether the pipe is full. And here we have that check. So inRead plus the pipe size, which is 512, if that equals the write index, then we've got a pipe full situation. That is shown in this picture here, where inRead plus 512 is equal to inWrite. If we've got a pipe full situation, then we need to go to sleep. And we will use as the channel to the sleep function the address of the write index in the pipe structure. Okay? And readers will wake up using that channel. Remember that here's a pipe read function, and remember that when we do a wake up, we wake up on the write index for the pipe that we want to wake up. Before we go to sleep, though, it may be that we have some readers that are waiting, and so we need to wake up any sleeping readers. It may be that this loop has looped through. We might have started with an empty pipe, and the readers were waiting to be awakened, and n may be a very large number, greater than 512, and we may have executed this loop enough times to fill up the pipe, in which case we need to go to sleep because the pipe is full. But we've got readers that went to sleep when the pipe was empty. So we need to wake up any readers that are out there first before we go to sleep. Okay, assuming that the pipe is not full, then we can go ahead and move a byte to the pipe. So that's what's happening here. We use the copy-in function to copy bytes from a virtual address space, as described by this page table here, to some place, that's the local variable ch. And where are we copying from? Well, it's the virtual address plus the number of bytes already copied, and we're moving 1 byte at a time. And if anything goes wrong, then we abort the pipe write function with however many bytes we've successfully copied. We break out of this loop and return the number of bytes we've copied so far. But assuming everything's okay, then we've got a byte from the user's virtual address space, and in this next line, we move it into the buffer for this pipe. So we are using the write index, and we are taking it mod 512, the pipe size, and we're moving the byte into that location in the buffer. And we are then incrementing the write index as well as incrementing I, and then we loop back. Now, after we're done filling the pipe, there may have been some readers that were sleeping, and so we need to issue a wake-up call. And again, we're issuing the wake-up call using as the channel the address of the inRead index, which is what any sleepers for this pipe will have gone to sleep on. And finally, we release the spin lock for this pipe and return the number of bytes that we've transferred. Finally, let's look at the pipe close function. Remember that from time to time, a user process will call the close system call, providing a file descriptor, for example, file descriptor number 2. And what that means is the user wants to remove this pointer and eliminate this file from this process. There is a reference count associated with each of these file objects, and if it does not go to 0 when we eliminate this pointer, then we don't do anything. But eventually it will go to 0 when there are no more pointers to the file object. And at that point, we need to return the file object to the free pool and eliminate this pointer here. And so at that point, we will call the pipe close function on this object here. So whenever we close the read end or close the write end, we will call this pipe close function. So let's take a look at it. It is passed a pointer to the pipe structure and a flag to indicate whether we are closing the write end or the read end. And so that's this argument here. We begin by acquiring the lock for the pipe object, and then if we are closing the write end, then we will set the write open flag in the pipe structure to 0. Okay, again, that's this one right here, to indicate that we have lost the pointer from the file object that's associated with the write end. Now, there could be readers or processes that are reading, and they are waiting because they found that the pipe was empty, and so they're just waiting for something to go into the pipe. So we need to wake those up. Remember that a reader will be sleeping if it finds that the pipe is empty. So going to the pipe read again, we see that if the pipe is empty, then we will be sleeping. But we also check to make sure that we do have a writer. And if we eliminate the write end, if we close down the write end, we need to wake this sleeping reader back up, and it will check, and then it will find that there is no write end open, and it will go ahead and return 0. So that's what's going on here. If we're closing the write end, we set the flag to 0 to indicate that we do not have any write end, and we wake up any waiting readers. On the other hand, if we're closing the read end, then we set the read open flag to 0 and wake up any sleeping writers for the same reason. Finally, if we have closed both the read end and the write end, in other words, if now both of these flags are 0, then we are done with the pipe object altogether. So at that point, we release the lock and call kfree to return the page that contained the pipe object back to the free pool of pages. If there's still one of the ends open, then we will just release the spin lock for this pipe object and return. Okay, that's it for pipe.c. I will see you in the next video.